Hi everyone. In this example problem, we're going to use the loop and junction rules to determine the current everywhere in this relatively complicated multi-loop circuit. By relatively complicated, I mean that there's no way to group these resistors into some overall equivalent resistance and to group these power supplies into some overall equivalent power supply. That is, to solve this problem, that is to find the current everywhere, we're going to have to systematically use the loop and junction rules. So to get started, let's assign unknown currents to the currents in these branches. So we'll call the current in this branch I1, we'll call the current in this branch I2, and we'll call the current emerging this way I3. Now if we've incorrectly guessed the direction of the current in any of these branches, that's no problem. Let's say I3 comes out negative. If I3 comes out negative, then we know the current in this top branch actually flows from right to left. So that's no problem. Okay, so let's apply the junction rule to this junction labeled A. We have I1 flowing in, I2 flowing in, and I3 flowing out. So the current flowing in must equal the current flowing out, so we'll have I1 plus I2 equals I3. Now let's apply the loop rule to this loop right here, which I'll call A, D, E, F, A. And I'm going to traverse the loop in that direction. Starting at A, we gain I2 times 4 ohms as we traverse the 4 ohm resistor against the direction of I2. We gain 14 volts as we go from low potential to high potential across the power supply. And then we drop I1 times 2 ohms as we traverse the 2 ohm resistor in the direction of the current. Now let's apply the loop rule to another loop starting at A, but this time we'll go from A to B to C to D and back to A. So we're going to apply it to this top loop in that direction. Starting at A, following this direction, we drop 6 volts as we go across the 6-volt power supply from the high potential to low potential. So that's a potential change of negative 6 volts. Now we're following I3. We're going across the 12 ohm resistor in the direction of I3. So we drop I3 times 12 ohms going across the 12 ohm resistor. And then going this way, we traverse the 14 volt power supply going from high potential to low potential. So we subtract another 14 volts there, and finally we go across the 4 ohm resistor in the direction of the current I2. So we drop, that is we subtract I2 times 4 ohms, and we're back to where we started, point A. So the total change in potential around this loop must be 0. Now we can combine the negative 6 volts and the negative 14 volts, and that gives us negative 20 volts. And for I3, we can substitute I1 plus I2. We can then distribute this through. We'll have minus I1 times 12 ohms and minus I2 times 12 ohms. And the minus I2 times 12 ohms we can combine with the minus I2 times 4 ohms to get minus I2 times 16 ohms. So now we have two equations with two unknowns. We have unknowns I1 and I2. Now, there are many different ways to solve this system of two equations and two unknowns, but one nice way is to note that if we multiply both sides of this equation by 4 and add it to this equation, and then we add both sides of both equations, we will then eliminate I2. So let's see how that works. Let's multiply both sides of this equation by 4 and put the corresponding terms under this equation. Comparing term by term, 4 times 0 gives me 0. 4 times 14 volts gives me 56 volts. 4 times negative I1 times 2 ohms gives me negative I1 times 8 ohms. And 4 times I2 times 4 ohms gives me I2 times 16 ohms. So now let's add both sides of the red and blue equations together. This eliminates I2 as promised and gives us the black equation in the green box. And if we solve that for I1, we get 1.8 amps. Plugging I1 back into either the red equation or the blue equation allows us to solve for I2, and I2 comes out to be negative 2.6 amps. Finally, plugging both I1 and I2 into our junction rule expression allows us to get I3, which turns out to be negative 0.8 amps. Let's put these results over here and talk about what they mean. I1 came out positive, so that means that the current in this branch here is actually in the direction that we guessed. So we have current of 1.8 amps flowing from right to left across the 2 ohm resistor and into junction A. I2 came out as negative 2.6 amps. So instead of having a current flowing this way, we actually have a current flowing in this middle branch from left to right of 2.6 amps. I3 also came out negative, a negative 0.8 amps. So what that means is we have, instead of a current flowing this way, we actually have 0.8 amps flowing from right to left in the top branch. Finally, we can check our answer by using another loop that we haven't used. We could use a loop around the full outer perimeter of this circuit. So we could go from A to B to C to D to E to F back to A. Let's apply the loop rule to that loop. Starting at A, we drop 6 volts going across this power supply from the higher potential to the lower potential. So we have negative 6 volts. We then go across the 12 ohm resistor in the direction of I3. So we drop I3 times 12 ohms. And then, continuing on, we go across the 2 ohm resistor in the direction of I1. So we drop I1 times 2 ohms as we go across the 2 ohm resistor in the direction of I1. And that takes us back to A. The total change in potential around this loop should be 0. And if you plug in for I3, which is negative 0.8 amps, making this actually overall a positive number. And for I1, the 1.8 amps right here, making this still negative, you will get 0 equals 0. And you should check that. Okay, thanks for watching. I hope this example has helped everyone to better understand how to use the loop and junction rules to analyze multi-loop circuits.